My name is Dr. Mahender. So I'm working as assistant professor in Institute of Aeronautical Engineering College. So today my topic is nanochemistry. So my objectives of this class is synthetic routes of nanomaterials, a bottom-up approach, and top-down approach. Okay. So we have also discussed what is a bottom-up approach and what is a top-down approach, and these two are bottom-up approach and top-down approach. These both are synthetic methods of nanomaterials. So we know that nanomaterials can be synthesized by two ways: bottom-up approach and top-down approach. So bottom-up approach means when the material is synthesizing itself, so we'll convert that material into nanomaterial. And top-down process means already the materials are existing in the nature, and that materials we are bringing down to the nanomaterial. So we are, and simply we can say bulk materials are converted into nanomaterials is called top-down process, and bottom-up approach. So we'll call as synthesis of nanomaterials by its from bottom means in this bottom-up approach. So we'll take one precursor and some suitable solvent, and we give some suitable conditions in such a way that it will form the nanomaterial. So we'll also see what are that methods. So and also we know that nanomaterials means the materials which is having the 1 to 100 nanometers. So we have also last class also we have discussed one-dimensional nanometers, two-dimensional nanometers, and three-dimensional nanometers, right? So one-dimensional nanometers can be measured in only length, breadth, or height. So two-dimensional length and breadth, and three-dimensional length, breadth, and the height. So three can be measured, that is called. And we have also seen this characterization. Characterization SIM, a scanning electron microscope, transition electron microscope, and scanning tunneling microscope, atomic force microscope. So we have also discussed about, and these are the main characteristics. As well as from these characteristics, so there are another important characteristics, that is XRD. So XRD is also one of the main factor to decide the particle size. And we also know that whenever we are speaking about nanochemistry means mainly the size of the particles. So when we are bringing down the size of the particle to the nano size, the properties, the optical properties, chemical properties, physical properties like melting point, boiling point also will changes, and also conductance properties also changing. We have seen in the last class. Okay, so based upon the synthetic route methods, there are various techniques are available. So the main characteristics when we have synthesized the nanomaterials are SEM. So SEM will give the picture of the materials, and in what size. Maybe that is a two-dimensional. How which dimension it is? Maybe one-dimensional, two-dimensional, or the three-dimensional. So we have also discussed one-dimensional nanomaterials means it may be surface coating. One-dimensional materials means it may be surface coating, and two-dimensional nanomaterials may be nanorods or the nanowires. And what is the three-dimensional nanomaterials? So three-dimensional nanomaterials are the nanoparticles. Nanoparticles are the nanoclusters. Okay, and we have also seen this when going to nano size. So what are the properties are going to change? Yes. So following the melting point, changing optical properties like that. We have also last class also we have seen this, and there are some properties also when the particle size is reducing from 10 to when the particle size is reducing, the properties of the chemicals are changing, and the properties of the material also changing. We have also seen how the surface area of the nanomaterials will change. Okay, so in this one we'll see bottom up approach and top down approach today. Okay, and also we can see in this one now for if you take a cube and if you cut into 8 pieces, So initially it is a 96 centimeter square. So when we bring into the 8 pieces, the area of this, the surface area, this one will be 192. So you can see there is a vast increase in the nanomaterial size. So in the nanomaterials, especially when we are using in the catalyst, so this will be very useful. Why means, suppose if the particle in a bulk, if it is a 96 centimeter square, and the same material if we bring down to the nano, it is coming to the 192 square centimeters. In some chemical reactions, a surface area plays a prominent role. So depending upon the surface area of the particle, so the reaction may be time taking for the reaction may be very fast, or it will be very slow. So that will depending upon the catalyst which will be used. But mainly in catalytical reactions, surface area plays a prominent role. So when the surface area plays a prominent role, this catalyst will be very useful. Which type of catalyst this is? As we are using the nano catalyst, so this will be very very useful. Instead of 1 kg of normal bulk material, if we are using, even then if we use the 250 grams of the nano catalyst, that will be very useful. And these are the synthetic methods. Okay, synthetic methods of nanomaterials. These are bottom up approach and the top down approach. Bottom up means small to the big method, and top down means big to the small. And we see what are the process, what are the methods. There are so many methods available for synthesis of nanomaterials. So the main in this one is bottom up nano fabrication, or small to big. So the atoms are converted into nanoparticles. Okay, atoms or the molecules are converted into nanoparticles. Simply, the definition of bottom up nano fabrication is atoms or molecules are converted into nanoparticles. So first we'll see chemical vapor deposition is one of the technique, and sol gel method, and the chemical reduction method. Okay, there are so many methods, but these are major methods or familiar methods which the nanomaterials can be synthesized. And we can see another bottom up approach. So next method, there are two methods. So first one, bottom up, and the bottom up approach, and top down approach. Again, the bottom up approach, chemical vapor deposition, sol gel, and chemical method. So first in this one, so we'll see these three methods today. How these materials are synthesized. So we'll see. So what is a chemical? First we'll see what is a chemical vapor deposition. Okay, chemical vapor deposition is a process that involves depositing of a solid material from a gaseous phase, often diluted in a carrier gas. So carrier gas, here the carrier gas will be used as nitrogen or the helium, or this may be used as one of the inert gas. So mainly helium or argon or nitrogen. Nitrogen or argon will be used as a inert gas material. So which diffuses from the PVD process, that the precursor or solid, with the material to be deposited being vaporized from a solid target and deposited on the substrate. So what is this chemical vapor deposition? So simply we'll say, what is the definition of this chemical vapor deposition means? Chemicals are converted into gaseous phase, and that gaseous phase are deposited on the substrate material. So that's why that's why the name is called chemical vapor and deposition. The chemicals which we want to convert into nanophase, that are preheated means that will be converted into gas phase, and that will be sent along with the inert gas. So there will be using of some inert gas. That inert gas will provide some mechanism so that the particles will be converted into nanoform, and again that gas phase particles will be deposited on the surface that is called substrate. That will be deposited in some surface that is called a substrate. So finally we'll get the nanoparticles will be deposited on the substrate. So and we'll see that are boats. So we'll see this is a systematical diagram. So we can see from this one, this is acetylene. This is acetylene. So this is called acetylene. Is a gas. Okay. So generally here, in this method, and which we are talking about, the acetylene is a gas. So generally, if we can also use the we can also use the liquids also. If you want to use liquids, we have to vaporize. We have to vaporize that liquid, and we have to send it into the send it into the CVD process. So we can see this one. It is made up of a quartz. This is made up of a one quartz. Yes, this pipe, this long necked pipe. So this is made up of a quartz. So which can withstand around 6,000 degrees centigrade, and this is made up of pure SiO2 or silicon dioxide. This is quartz. So we know that quartz is purely made up of silicon dioxide. Okay, and from this one it will be send nitrogen gas, and this nitrogen gas will be maintain some temperature. So you can see, so depending upon the particles we want to synthesize. So here the major source of the element is acetylene, and here the gas which we are using is inert gas. So inert gas is nitrogen. Here instead of nitrogen we can also use a argon. So argon or nitrogen can be used, but in the diagram it is showing nitrogen. But generally this chemical vapor deposition method using acetylene as a precursor gas and nitrogen as a inert gas, and we can see this one. This one is boat. This one it is called a boat, and sometimes this is called a boat. So this is acetylene gas and passes through this chamber, and here there is a substrate. Here suppose sometimes SS mesh will be used. That SS mesh will be coated with some acids, so that these gases may get deposited on the boat, and this boat here will collect the nanoparticles. Here will collect the nanoparticles, and from this one we'll get the outlet gas. So what is the outlet gas? And another important thing we can talk in the chemical vapor deposition method. Here this method, what the materials it is using, acetylene will be used as a precursor material, and nitrogen will be used as a inert gas. So always in this process, always the nitrogen will be processed from the this quartz oven. So this is called oven. So this is a oven which will maintain the temperature of 720 degrees centigrade. So when it maintains the temperature, this acetylene will be used as a carbon source. C2 C2H2 will be used as carbon source. C2 will be used as a carbon source, and nitrogen will be, we know that nitrogen is an inert gas. It does not take place any chemical reaction. So what will get the final product here? What will get the final product? This carbon. So the main aim in this chemical vapor deposition is synthesis of carbon nanomaterials. Synthesis of carbon nanomaterials, or this synthesis of carbon nanomaterials may be the carbon nanomaterials may be the fullerenes, or the carbon nanotubes, or the carbon nanowires, and the accumulation of the wires or the tubes or the fullerenes, that will depend upon the substrate. Here this is a catalyst. So this is also called as a catalyst or the substrate. Catalyst or the substrate which will use to deposit on the surface of this one. So generally we'll take some iron mesh. So we'll take this iron mesh. This is made up of iron. So why we'll take only this iron? So this iron will be used as a catalyst. So this iron will be used as a catalyst where suppose these will come as a vapors, and it will be deposited on the surface of the substance. So this one is called boat. Here it is written, this is a quartz boat. Quartz boat means it's a made up of SiO2. And what we can expect, what is the outlet of this one? Outlet of this one is uh, only the hydrogen. So here we'll get the outlet as a hydrogen and plus some from some unconverted acetylene. Some unconverted acetylene also will get out as a output. So this output can be output can be escape into the vent, so that we'll get here the nanometers. So and another important thing in this chemical vapor deposition method is this carbon. So only we can also use the acetylene, we can also use the propane, we can also use the methane. So we can also use the methane also. Why we can use methane, and why, what is the difference between the acetylene? So what is our aim in the chemical vapor deposition method is to get the carbon nanomaterials. So to get the carbon nanomaterials, actually what is the principle and what is the mechanism involving in the chemical vapor deposition means this acetylene is cracking, or this acetylene is breaking down. This acetylene is breaking down into carbon nanomaterials. And when this acetylene is breaking, but it is forming the carbon nanometers. When the carbon nanometers is forming, we are giving some catalyst. So we are providing this quartz boat plays a prominent role. In the quartz boat, we'll keep some catalyst. The catalyst, like we can keep some metals. Nickel will be used as a best catalyst, and we can also use the platinum. We can also use the platinum, palladium, and we can also use the iron. So iron, so that why the formation of the nanoparticles or carbon nanoparticles will be depending upon this precursor, which this catalyst. So we'll call this catalyst which we are using. So depending upon the catalyst, the particles will be formed. And another important factor is also depends upon the temperature of the oven we maintain. Temperature of the oven we maintain, and at this temperature, suppose if at 720 degrees centigrade, if carbon nanomaterials are formed, if we decrease the temperature 650 degrees centigrade, at the temperature of 650 degrees centigrade, it will not form the carbon nanomaterials. Maybe it will form the amorphous carbon. So by controlling the temperature of this oven, we can control the particle size. So that's why this process is also called as tailor-made properties. So tailor-made properties means we'll study by sending we study by taking different temperatures. First, we'll take the 600 degrees centigrade, and we'll run the experiment, and we'll go for XRD analysis, we'll go for SEM analysis, and we'll go for TEM analysis. First of all, whenever we synthesize the nanoparticles, the first analysis what we have to do is the whether we got the a nanopowder or amorphous. So first basic thing what we have to analyze is XRD. What we have to analyze is XRD means X-ray diffraction. So X-ray diffraction will give whether what we got. X-ray diffraction will give the powder which we got amorphous or the crystalline. So always if we say there is a nanoparticle means we should not get the amorphous. We should get the crystalline particles. Then only all the nanoparticles will be in a crystalline phase. So now what we'll do in crystalline phase? Means crystalline particles is there means that is a nanoparticles. And after in this process, once you synthesize the nanoparticles, so what we'll do? We'll send the acetylene through this, and we'll send nitrogen. whenever we are passing the precursor, the nitrogen, before starting this CVD process, we have to send 5 minutes or the 10 minutes continuously to the inert gas. So why we have to pass the nitrogen inside this? So we have to create some inert we have to create some inert atmosphere inside the tube, inert atmosphere inside the tube, so that there is a no oxygen will be there. There is no continuously, if we are process the nitrogen continuously, we can process the nitrogen. So what will happen, if any amounts of oxygen will be there, that can be went out, and then slowly what we have to do, slowly we have to release the we have to release the acetylene. When the acetylene is released, so on what factors the nanoparticles will be depend? The first factor is the catalyst which we are using. On what factors, whether the nanoparticles, formation of the nanoparticles will be depends upon, the formation of the nanoparticles will be depends upon the first one. What are the factors, whether the first one is precursor material. First one is precursor material, and second one is CVD temperature. CVD temperature. And third one is what is the third one? Catalyst. And these three factors will these three factors will decide whether the carbon whether the carbon nanomaterials are fullerenes, or the carbon nanotubes, or the carbon nanowires. So these three factors plays a prominent role. So generally the catalyst will be used as iron and nickel, and sometimes they also use a copper, and they will use as a palladium, platinum, and palladium. So these five catalysts will be used as a these five metals. Generally, all the the metals will be used as a catalyst. And what is the precursor material here? Maybe carbon source. Maybe carbon source. Carbon source may be acetylene, C2H2, or propane and propylene, and LPG, and also methane also can be used. So depending upon the material we want, so we can use the material. So the CVD mainly depends upon the precursor and CVD temperature and the catalyst. So generally this will be operated at above 500 degrees centigrade. So you can see here in the CVD diagram, I will show you the main components. The main components of this one is here. This one here we can also use the methane. Here we can also use the argon. So here the temperature varies with required material. Okay. So, and before that, here how and another important thing on what factors the formation of this nanomaterial, and the flow rate, and this mainly depends upon, and what flow rate, this flow rates, this precursor flow rate, precursor flow rate will be monitored by flow meters. Okay, so depending upon the flow rate, depending upon the flow rate of this precursor gas which we are sending, flow rate of both the precursor and the inert gas. So depending upon this one, the particles may be changes. So what are the output of this particle? What are the output particles we are expected from the chemical vapor deposition method? So chemical vapor deposition method. So first one, what are the output materials we'll get? Is first one. There may be carbon nanotubes. Okay, carbon nanotubes. And second one, fullerenes. fullerenes, and third one carbon nanowires, carbon nanowires, and fourth one is carbon or graphene. Graphene. Okay, so we may get these four types of carbon nanomaterials, and these four types of carbon nanomaterials, four types of these carbon nanomaterials will be formed depending upon the what are the factors: flow rate of the precursor gas, and the type of the precursor, maybe acetylene, maybe propylene, or depending upon which we have taken, and also the flow rate of the precursor and flow rate of the inert gas also, and also temperature, and also another factor is temperature of this process. Temperature is one of the factor, and second one is catalyst which we'll use, and catalyst. So based upon these factors, this process whether we'll get the carbon nanomaterials. What are the carbon nanomaterials? Carbon nanotubes, nanowires, or the nanoparticles, and fullerenes, and sometimes also we'll get the graphene. Sometimes also we'll get the graphene, and this is about the CVD process. And another one important thing, when we get the nanomaterials from the CVD process, so what we have to do is purification of these carbon nanomaterials will be very important. So why the purification of the nanomaterials will be very important means, so whatever sometimes, so in this process, when the precursor gas is going like this, the temperature in this one only, the temperature here, the main, this is called the core temperature, and here the whatever the particles will be formed here will be all 720 degrees centigrade, and from here it may be less than it may be less than slightly less than 700 degrees centigrade. So what will happen in this process, so there may be some amount of amorphous carbon will be formed. So this amorphous carbon will be removed by some purification method. So this purification method, so what are the purification method of purification method is, generally this amorphous carbon can be removed by taking aqua regia, called when sulfuric acid and nitric acid both are mixed and it is dissolved in the amorphous carbon. So when we get these products, so what we have to do, these products, when we are treated with aqua regia, all the amorphous carbon will be oxidized, and only whatever we get the material that is a nano form, maybe that fullerenes or the nano rods or the nanowires. Okay, so the purification method is compulsory, and another important purification method for nano materials are calcination. So we'll be taking the muffle furnace, and we are keeping above the 650 degrees centigrade. We know that at 650 degrees centigrade, so carbon will be oxidized. So that carbon will be oxidized, but the material which we have is not a carbon, that is a nanomaterial. But if the nanomaterials will not be oxidized at 650 degrees centigrade, for this purpose, we'll take the material which we are getting the CVD and will keep in a muffle furnace, so that what will happen to this one, if there is a amorphous carbon that will be oxidized, only amorphous carbon will be oxidized, remaining the nanomaterials. So in this method also we can also purify the nanomaterials, but always 100% purity will not be obtained from this process, but we need further techniques for purification. Further purification method is treating with aqua regia, and another one is calcium. What is the applications? So a typical thermal activated CVD process involves, actually what are the steps involved in this one. Okay, first we'll see what is the steps involved. First one, mass transport of precursor in the form of vapor to the substrate surface inside a chamber. First the mass transfer will take place into the chamber. Okay, then adsorption of the precursor on the surface of the substrate. Adsorption on the precursor. First the mass transfer will take place here. The first mass transfer will take place, and adsorption. Second one, adsorption of this mass takes place on the precursor. Here, this is a precursor. Okay, the second step. And third one, chemical reaction on and near the substrate surface. Chemical reaction means chemical reaction on and surface of the substrate. The third one, chemical reactions on and near the substrate surface. So next one, deposition of the chemicals on the substrate. Last process, deposition of the surface of the substrate. Once it is deposited, then we'll collect it and we go for the some purification techniques. Okay. So next class I will continue for the sol gel method. So next class we'll see the sol gel method, and these are the references I have been taken. What are the references? Are Essentials of Nanochemistry by N. Kumar, and Introduction of Nanoscience and Nanomaterials by Dinesh C. Agarwal. This is the Indian Institute of IIT, India, right? So, and the third reference I have taken, An Introduction to Nanomaterials and Nanoscience by Asim K. Das CBS. So, next class, I will next video I will discuss sol gel method. So, what is a sol gel method and what are the applications? And what are the applications of this CVD method? So CVD method applications is also same as from which source you have been synthesized the carbon nanomaterials. The usage of the carbon nanomaterials will be the same. Only the method will be the different, but by usage and the application will be the same. So next class we'll see what is a. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.